All right, so what is conditional probability? Your book says the probability that an event will occur given that some other event has already occurred or is certain to occur is a conditional probability. So something like, what if given that it's raining outside, what is the probability that someone has an umbrella? So it'd be something like that. So you give a condition, and then you're trying to figure out the probability given that condition. And the way that you can write that symbolically with symbols, you write probability A and then this line right here and then B. So what this means is, this is the probability of A given the occurrence of B, or the probability of A given B. And the formula is the probability of the intersection of A and B divided by the probability of B. Again, in words, this is the probability of A given the occurrence of B. As long as we follow the formula, we can get these problems right. So let's look at, this is the fourth slide on page 1 of section 6.3. It says, suppose a marketing research firm has surveyed a panel of consumers to test a new product and produce the following cross tabulation indicating the number of panelists that liked the product, the number that did not like the product, and the number that were undecided. Okay? So we have age groups there. We have if they liked it, if they did not like it, if they were undecided, and we also have the total of like, not like, and undecided on the right. All right, the problem is if an individual is between 35 and 50, hey, that's me. What is the probability that he or she will like the product? Okay, so the probability of, well, let's let A be you like the product. And the given part, what was given, let's let that be B. It said if an individual is between 35 and 50. So that's given. And we're trying to figure out the probability of A given B. All right. So let's go over here to the table, and we want to look at the column. The row that's 35 to 50. All right, so what is the probability that we're given 35 to 50 and the probability that that person would like the product? So the part over total, how many like? Again, look at the row 35 to 50. How many does it say like the product? 193. That's out of how many? What's the total if you go over to the right? 444. All right. Now, what is the probability of B? B is the age between 350, actually, it's 193 out of the entire total. What's the entire total? 1403. Not just the total of 35 to 50, but the entire total of people that were surveyed. All right, now let's figure out the probability of being someone between 35 and 50. Well, there are how many total in that entire row? 444 out of 1403. So what we're doing now is we're working this thing by definition. Okay? So this right here is the probability of A intersection B, and this right here is the probability of B. Now I would flip and multiply there, and I would get 193 over 1403 times 1403 over 444. That would cancel out, and I would be left with 193 over 444. All right, if I was to divide that in a calculator, I could get a decimal. 193 divided by 444. All right, so you could round that if you wanted to ever how many places it asks you to. It's about 0.43. Now, that's the hard way to work the problem, believe it or not, by just following the definition. The easy way to work the problem, because if you're a mathematician or you've done a lot of math, we always look for shortcuts. The easy way to work this problem is go back to the table. Everybody look at the table. The number of people that like whatever we're looking at between 35 and 50, the age of 35 and 50 is 193. Look how many total there is in that column, 444. So it's the number that I actually wrote down first. It's 193 out of 444. Either way gives you the same answer, but which way is easier? The second way, right? You just look at the table and you assume, you say in your mind, well, we know that we're only looking at people between 35 and 50. Of those, 193 out of 444 like that product. So that's your probability, 193 over 444. Even though either way gives you the solution, there is an easier way to do it. In this case, using common sense. I was trying to use common sense earlier. We were going over a problem and I was counting with my fingers and all. That was probably the longer way. In this case, common sense gives us a shorter way to do this. And I say common sense, it's really math sense too. All right, let's look at the next example that's given in the PowerPoint. It's on page 2 of the PowerPoint that I gave you. It says, out of 300 applicants for a job, 212 are male. Of the male applicants, 150 have served in the military. All right, so for me to make sense of this word problem, I got to think of it. So I have 300 total. It says out of that 300, 212 are male. And then out of the males, it says that 110 have served in the military. All right, so we can actually get a lot more information from that if we wanted. We could get how many females there are in the application, or in the, because we just simply would say 300 minus 212 when we get the number of females. Do we need that? I don't know. I haven't read the rest of the problem. We could find out how many are not in the military, right? But if I know that 115 had military experience, then I say 212 minus 110, and I get, what, 102. That means 102 were not in the military. Do I need that to work the problem? I have no idea. I haven't read the rest of the problem. I'm just trying to make a point that we can figure out other things from the total set, by what information is given to us. We could figure out the number of females. Now, one thing I couldn't figure out is how many females were in the military out of that, because it doesn't say anything about that. Anyway, let me read the rest of the problem. A, what is the probability that a randomly chosen applicant has served in the military given that he is male? The easy way to work this problem is to look at the number of males, look at the number of military males. So what is part over total if I'm given that they're a male? So we know we're looking for the probability that they are in the military given that they're male. All right. We can follow the formula, and this is going to be harder. We can use math sense, and it's going to be easier. So how many total males were there that applied? 212. That's the total males. How many of those were in the military? 110. That's the answer. Okay, so in this case, using a little math sense, writing some stuff down makes this a lot easier. So I divide and probably get a decimal. So about 52%, about 0.52. Part B says, if 152 of the applicants have served in the military, what is the probability that a randomly chosen applicant is male, given that the applicant has served in the military? All right, so we were just given the total number of military people out of the 300. All right, so we were just given the total military. We were told that there were 152. So I guarantee you, part over total, the bottom is going to be 152. Now we're looking for the probability that a randomly chosen applicant is male. So how many males were in the military? 110. All right. So given that the selection will be from the males, we know that 110 of the military out of 152 of the total is what we're looking for. So that's not men, male. So the probability of male, given that you know the total number of military, and I don't know what that is. I have to divide. Now, if you look in your PowerPoint, they're going to explain to you how to use the formula and get the same answer. You say, what do you want? Well, I want you to be able to work out the problems. So I would say do the way that's easiest for you. Okay. All right, now, I'm trying to see. It looks like we're getting into the multiplication rule for independent events. Now, that's the second part of this section. That was the addition rules. And the conditional probability rule. That's what we've done so far. Now the multiplication rule. So as long as the two events are independent, that means one doesn't rely on the other. Or just because I flip ahead the first time, that doesn't mean that I have less of a chance to flip ahead the second time, right? So as long as the events are independent, define the probability of more than one event, or the intersection of the events. That's the probability that the first event happens times the probability that the second event happens. Alright, so for example, what if I wanted to know the probability that if I randomly selected a female from this class, they would be wearing a pink shirt. Alright, so I need to know, this would be the probability if I randomly selected someone from this class that they are female and they are wearing a pink shirt. So let's see how many people are in here. We have 23 people here today. Okay, so the probability first that if I randomly selected someone that they were female, we have 23 people and $16 females. So there's the probability that if I randomly selected someone from this class, let's say that I put a blindfold on and I just started stumbling around and I grabbed somebody, which I wouldn't do, then that person would be female. All right, 16 out of 23. Now, what is the probability that the female is wearing a pink shirt? Well, let's just say the person's wearing a pink shirt. I only see one person with a completely pink shirt on in here. No names will be called. So that's 1 out of 23. So the probability that if I randomly selected a person in this class that they would be female and wearing a pink shirt would be 16 out of 23 times 1 over 23. So that's 16, times 1. I'm not going to do that. That would be embarrassing. 23 times 23. So 16 out of 529. Now, I didn't use conditional probability saying that I know they're female in a pink shirt. That would be different. But Yeah. That may not be the best example, by the way. We'd really want the two events to be completely independent. So let's say I wanted to know what's the probability if I had a single die and a deck of cards. What's the probability of rolling a 3 and selecting a heart from a die and a deck of cards? Independent events. They don't happen at the same time. Okay? So first, what's the probability of rolling a 3? Well, it's going to be the probability of rolling a 3 times the probability of selecting a card that's a heart. So the probability of rolling a 3 is 1 out of 6. The probability of selecting a heart is 13 out of 52. So if I do those two things, the probability would be, I gotta say, well, 6. You can reduce one of those fractions to make this easier, right? Can you reduce one before you multiply? 1/6 and what? 1/4. So that's 1 out of 24. And you can make that a decimal if you want. But there is a very small chance that if you roll, I can tell you. You don't believe me? When you go home, if you have a die, a single die, and a deck of cards, let's see, 1 divided by 24. So there is a 4.1% chance. So it's only going to happen about 4 times out of every 100 times you do it, or about 1 time out of every 25 times you do it. Will you roll a die and get a 3, and then if you have your deck of cards, randomly pick a card and get a heart? Now, it may happen on the first try, but more than likely it's not. It's just a little over 4% chance. Now, you can have more than 2 events. You can have 3 events, 4 events, 5 events. So like if I want to know the probability that if I roll a coin 3 times, I get 3 heads in a row. Probability of getting a heads in one, roll a heads in another roll, and a heads in another, if I'm flipping a coin. So what's the probability the first time of getting a head? 1 out of 2. What's the probability the second time getting a head? 1 out of 2. Guess what the probability of the third time getting a head is? That's right, 1 out of 2. So that's 1/2 to the third power, or 1 out of 8. So about 1 out of every 8 times, if you flip a coin 3 times in a row, you'll get heads, heads, heads. That doesn't mean exactly 1 out of every 8 times, but that's the probability. So because each one of those events are independent. You know, the second flip doesn't depend on the first flip, maybe unless you hurt your thumb. But then still, if you have a hurt thumb, you're still going to flip it, so I guess not. One of the examples that your PowerPoint goes through is about a case. It's about, listen to this. On June 18th, 1964, at about 11:30 a.m., Miss Juanita Brooks was assaulted and robbed while walking through an alley in the San Pedro area of Los Angeles. Imagine that. Miss Brooks described her assailant as a young woman with a blonde ponytail. At about the same time, John Bass was watering his lawn and witnessed the assault. He described the assailant as a Caucasian woman with dark blonde hair. As she ran from the alley, she jumped into the yellow automobile driven by a black man with a mustache and a beard. Several days later, the police arrested 2 individuals based on the descriptions provided by the assailant and the witness. The 2 suspects were eventually charged with a crime. During the trial, the prosecution called a professor of mathematics to testify. The prosecutor set forth the following probabilities for the characteristics of the assailants. All right, so you got a little chart. If you look on page 5, this is in your PowerPoint for 6.3. So the probability of someone having a yellow automobile, 0.10. A man with a mustache, 0.25. A girl with a ponytail, 0.10. A girl with blonde hair, 0.33. A black man with a beard, 0.10. An interracial couple in a car, 0.001. So that was at that time in LA. It says if the events are assumed to be independent, then the product rule can be used to calculate the likelihood of observing their joint occurrence. So the probability of a yellow automobile and a man with a mustache and a girl with a ponytail and a girl with blonde hair and a black man with a beard and an interracial couple in a car is 0.000000825. So based on the product rule, the mathematician testified there's about a 1 in 12 million chance that the couple selected at random will possess these characteristics. The prosecution added that the probability was the chance that any other couple possessed the distinctive characteristics of the defendants. The jury convicted the defendants on appeal. The Supreme Court of California reversed the decision based on 2 main points. First, there was no proof offered that the probabilities used in the probability calculation were correct, and there was no evidence that the events were independent. Second, the prosecution's evidence pertaining to a randomly selected couple was not pertinent to the problem of the existence of any other couple possessing the same characteristics. So, kind of interesting. Tried to use probability. I guess it worked. I don't know. It was overturned by the Supreme Court. So. All right. Remember, sometimes if we know the probability of something happening, and we're trying to figure out the probability of something not happening, how do we figure that out? Sometimes in these word problems, we're going to have to use the fact that the probability of something not happening is equal to 1 minus the probability of it happening. And I didn't use good notation there. It's P of A hat, or A bar, equals 1 minus P of A. So if you're working out a probability problem and you're given one probability, but it's asking you for the thing not happening, then you are going to have to say 1 minus the probability of it happening. There's another example in your PowerPoint that talks about the probability of parts being non-defective. It's at the bottom of page 5. And they wanted to know, okay, so you have all these parts that go into a product, and you have the probability of them all being non-defective. If you want to know the probability that all 4 parts are defective, then for each one of those, you're going to have to say 1 minus. So look where it says the probability of A. This is the bottom of page 5 on the left. If the probability of A is 0.9, and that's for a non-defective product, then the probability for it being defective is 1 minus 0.9, right, or 0.1. So if we're trying to figure out the probability that all 4 parts were defective, we have to do that for all 4 of those parts in the problem. So the probability of not A is 0.1. The probability of not B would be 1 minus 0.7, which is 0.3. The probability that C is non-defective, it gives us, is 0.8. So the probability it's defective is 0.2. And then part D, it says, has a 0.9% chance of being non-defective. So the probability of it being defective is 0.1. Now, if I want to know the probability of all 4 pieces being defective, I'm going to have to say 0.1 times 0.3 times 0.2 times 0.1. All right, so your book went ahead and did that for us, I think. Maybe, maybe not. Let me look. PowerPoint, are you working with me or against me? It's working with me. Good. It got 0.0006, or a 0.06% chance of being defective. Okay. So that's a good. That's not a very good chance of being defective, I would think. That's what, 6 out of 10,000. So sometimes we do have to use those complements to figure out probabilities. All right, you should have all of the skills that you need for 6.3. However, probably not 6.4. So we will finish up 6.4 on the next class meeting.